Hi, welcome to Special Maths Academy. My name is Honor Pius, and today we'll be looking at problem 5 of the International Mathematics Olympiad 2022. So this is a very short problem, a number theory problem. So we have A, B, P, positive integers. We want to find all triples, whereby P will be a prime and it satisfies this equation. Okay, so moving forward, we are going to assume that we have values satisfying this equation. We want to see what they could possibly be. So that's going to be the major direction of this proof. Once we found out what their possibilities, we just check them to see whether they actually work or not. And then that will give us the solutions we need. Okay, so first of all, we'll be assuming we have some A, B, P satisfying all the necessary conditions. So there are a few things to just get out of the way. So you might be familiar with some of them, but maybe not. So we just make sure we have them in place before we go proper into the solutions so that we can have a very smooth sailing. All right. So first of all, B factorial just simply means product of numbers starting from 1, 2, 3 up to B, right? This is going to be less than or equal to B times B times B, that number of times. So we have B values here. And so there are B terms, and each of them are less than or equal to B. So that will give us that this ultimately is less than or equal to B raised to power B. Also, if we observe from this, we see that we are going to have about half of the numbers. So precisely B over 2 of those numbers will be even. Okay, so from those even numbers, we see that each of them is going to produce at least a factor of 2 in B factorial. So if we look at if we collect all the powers of 2 that we can get from B factorial, it has to at least be as much as B over 2. So for instance, let's say we look at 7 factorial. 1, 2, 3, 4, 5, 6, 7. So we see that about half of them, which is 7 over 2, that's 3.5. So 3 of them would be even. So from that, we're going to get a factor of 2 here. Here we get actually 2 factors of 2, but we can just pick one, and we get another factor of 2. So ultimately, 2 raised to the power 4 divides this, but what we are saying is that at least 2 raised to the power 3 is going to divide this. So a way of representing this is by saying that the periodic evaluation of 7 factorial 2 has to be at least 3. So this is the power of 2 in 7 factorial. Okay, so we're going to make use of this somewhere along the way. Also, next, if we have that x doesn't divide some integer, positive integer, doesn't divide b factorial, then x has to be bigger than b. That's because we can do this by contradiction. Suppose not, then x will have to be less than or equal to b, and it's going to appear somewhere in this product. That's the factorial. So certainly x is going to be a factor of b factorial, and that will contradict the initial assumption. So we cannot have x less than or equal to b, and we come down to this conclusion. Next, look at this three set of values. Okay, so here we are assuming that Q is prime. So the claim here is that we cannot have exactly 2 of this. So this is coming from the equation we have above, which is A raised to power P is B factorial plus P. So if Q divides A, is the same as saying that Q divides A raised to power P. That's because Q divides A means Q divides A raised to power P clearly. But also if Q divides A raised to power P, then it has to be a factor of at least one of them. So it's already a factor of A as well. Okay, on the other hand, Q is less than or equal to B based on what we did. If Q is less than or equal to B, we have that definitely Q will have to divide B factorial because it's part of it. And if Q is greater than B, then we have that Q cannot divide B factorial. So the reason for this is because Q is a prime. So Q is a prime. So suppose Q divides B factorial, then it has to be a factor it has to at least appear somewhere, because the smallest multiple of q we could have is q itself. So if you have a multiple of q in this range, then q itself has to be there. So q will have to be at least b, have to be at most b, and that will contradict this. So we have that this is actually an if and only if condition. So once we have this, we see that these three conditions just simply means that the first one simply means that q divides a raised power p. The second one simply means that q divides b factorial. And of course, the third one means that q divides p, because they are prime numbers. So here we say that if it divides any two, let's say these two for instance, then it has to divide the third one, because we are making it subject and becomes like a multiple of q. So the same argument works irrespective of which two we actually start with. So that's the idea here. Okay. Okay, so now let's move to another idea that we're making use of, which is a way of bounding or estimating some values involving factorial versus powers. Okay, so the first one is if we are given p raised to power p, we're given p raised to power p minus p, then this clearly is going to be greater or equal to p raised to power p minus p raised to power p minus 1, because p starts from at least 2, right? And then from that we can factorize out p minus 1 and at least one value of p, and we are left with this. So we see that this is going to be greater than p factorial. Why is that? So remember, p factorial will be start from 1, 2. At some point we're going to get p minus 2, if possible p minus 1, and p. So from this we see that we already accounted for p and p minus 1, and we have these numbers left, p minus 2 of them. If p is 2, then we don't have anything left, and also this will be 1, so nothing to talk about. We have equality. And if it's bigger than 2, that's from 3 and above, we'll see that each of these are all going to be less than p, in fact, because they cannot be equal to p. So p will be greater than each and every one of them. So we are going to actually have a strict inequality here. On the other hand, something similar, but this is different. So here we have p raised to power 2p minus 1 is greater than 2p minus 1, or factorial. So what's the idea here? Here we're going to use AMGM. Okay, so actually what we're going to prove is this. So what we're looking at 2p minus 1 terms, which are just the consecutive numbers up to 2p minus 1. Okay, so if we take the arithmetic mean of this, it's just the average. This arithmetic sequence, so it's going to be in the middle. To get that, we can just add the first and the last and divide by 2. So see that is p. Okay, and then on the other hand, the geometric mean, we have to take the product, which is just 2p minus 1 factorial, and then so 2p minus 1 factorial, and then we take the root of depending on the number of terms, which is 2p minus 1. So we have this, and then when we raise both sides to 2p minus 1, we get the desired conclusion. Okay, so another minor stuff we need to get is suppose we have some x is less than y plus z, then we have that at least x is going to be less than 2y, or if not, then it has to be less than 2z. So to say this, once again, we use a proof by contradiction. So suppose not, then we must have that x is not less than 2y, so it's at least 2y, and at the same time also that x is not less than 2z, so it's at least 2z. If we add both of these inequalities, we see that 2x is greater than or equal to this, which will contradict the initial assumption divided by 2. Okay, so we're making use of this as well. All right. So the next step, we're going to look at a function or two functions very similar, so f and g. and we want to just get some basic ideas about the values of how it behaves for positive integers. Okay, so we're going to show that these functions are actually increasing for t greater than or equal to 2. So one simple way you can do this is just to apply calculus by differentiating and then seeing that the derivative will be positive. But we can also, since we are dealing with integers, we can also use induction. So we'll just compare one value with the next value of the function. So if you look at f of t plus 1, for instance, so f of t plus 1, that's just going to be 2 raised to power t minus 1. So if we subtract this from f of t, we're going to be left with 2 raised to power t minus 1 minus 1. And this is going to be positive. That's going to be strictly greater than 0 when t is greater than 1. So this is going to be greater than 0 for t greater than or equal to 2. So this means that this sequence is actually going to, like, you can look at this like a sequence starting from 2. It's going to be increasing. Okay, and also it's important to just note this, that f of 2 is equal to 0. So meaning beyond 2, the value is going to end up being strictly positive. In the same light, we can actually handle g of t. So very, very similarly, we have g. So let's do that up here. G plus 1 will be 2t minus 1 minus t minus 1. Okay, so if we take difference, you see the increment, we'll get that this is equal to, so this is going to be 4 times this value. So we'll get 3 times this when we take the difference, then plus 1. T will cancel out. Okay, so we have this. When t starts from 2 as well, you see that this is going to definitely be positive. In fact, this is always positive irrespective of the value of t. So in fact, this is always increasing. So we get this greater than or equal to greater than 0. And g of 2 in this case, once again, we'll see that it's going to be equal to 0. So the idea here is that beyond 2, for t greater than 2, the value of g is going to be positive always. So we'll need this towards the end as well. And then one final piece. So now for p odd, let's take k to be the periodic evaluation of p minus 1 over 2 at 2. So this means that k is like the highest power we can find in p minus 2. So that's we can write p minus 2. Of course, this is an integer because p is odd. So we can write this as like 2 raised to power k times some odd number. So that's when we pull out all the factors of 2. So that's the value of k that we are talking about. Okay, so we claim that if you look at the highest power of 2 we can find in p raised to power p minus 1 minus 1, then it has to satisfy this particular inequality, this particular equality. So how do we go about this? All right, so the idea here is that p minus 1 minus 1 is equal to p squared. We can write this as k plus 1 times m. So in the power minus 1. Okay. And now if you recall, when you have x raised to the power m minus 1, we can factorize this. So we're going to make use of this factorization. So now m is odd, meaning that this is even. And the power here is also even, that's x raised to the power 0. So ultimately here we can observe that this is going to be have an odd number of terms. Okay, so if x is also odd, then the sum of odd number of odd numbers is going to be odd as well. And in this case, we see that x, we can take x as what? P raised to power 2 raised to power k plus 1, which is clearly odd. So that will give us that the powers of 2 we can find here will all come from just x minus 1. So this means that if we take the periodic evaluation at 2, it's just the same as restricting it to just this portion. Okay. All right. So next, if we have x squared minus 1, you see that by difference of 2 squares, we get this. So if 4 divides x minus 1, then 4 cannot divide x plus 1. Otherwise, if you take the difference, you get that 4 will have to divide 2. So this is not possible. However, x must be odd. So 2 divides x plus 1. So meaning the highest power we can get from x plus 1 is just 2 itself. So what this means is that if you look at the power of 2 in x squared minus 1, it's just going to be 1 more than the power in x minus 1 itself, so long as 4 divides x minus 1. Okay, so we're just going to use this repeatedly. So for example, if we take this to the next, square that once more, so it's like replacing x by x squared, we're going to see that this will have 1 more greater than the previous one, because clearly since 4 already divided x minus 1, 4 must divide the consequent powers we'll be dealing with. So here we'll get that this would satisfy this as well, and ultimately we'll have is twice the base 1. So we just continue this inductively. So each time we square the value, we get 1 more factor of 2. Each time we square, we'll get 1 more factor of 2. So eventually, if we do this up to say 2k, then we should expect a total of k extra factors of 2. So this is just going to be what we will use here. This time around, x will simply be p squared. So I'll just need to check that the most fundamental part is satisfied. So just need to check that 4 divides p squared minus 1, which is by difference of 2 squares. We can factorize this, and they are both even. So clearly 4 will divide this, and we have the major piece we need. So this simply means that this will be k plus the evaluation at p squared minus 1. Okay. So so we have our k here. Now the evaluation at p squared minus 1, we saw that we could split into 2 parts, p minus 1 and p plus 1. So that's just what we did here. And we can simplify everything by remembering that k is this value, and we'll plug it to get this nice result. Okay, so there are different ways we could go about this, but yeah. So now we have all the ingredients we need to solve this problem. Okay, so let's get into the solution proper. Now, we'll start by, remember that we are assuming a raised to power p is equal to b factorial plus p. So this is our assumption. Okay, so first of all, suppose that a were less than p. Okay, so remember p is a prime. So clearly we know that a is not 1, because if we set a equal to 1, we'll get 1 is b factorial plus p. P itself is already greater than 1, and b factorial is clearly positive, so this is not possible. So since a is not 1 and it's less than p, and we know that p is prime, it means that a cannot be a factor of p. That's because primes have only 2 positive factors, itself and 1, and we know a is neither of those. Okay, so from this, we can conclude that that a doesn't divide p. So remember, remember that this will imply that a doesn't divide b factorial, based on the fact that if he divided b factorial and he already divided a raised power p, then he has to divide p, which is not possible. Okay, so from this now, we're going to use one of the initial stuff we got, that if x doesn't divide b factorial, then x has to be bigger than b. So this says that a will have to be greater than b. Of course, a itself is already less than p, so we have this this order. Okay, so next we'll have that a raised to power p, which is b factorial plus p, it's going to be less than b raised to power b. So this was an earlier estimate we can make use of here, which is less than or equal to, actually strictly less than a raised to power b, a raised to power a minus 1. Okay, so what did I do here? So a is greater than b, and that means that a minus 1 is greater than or equal to b, since we are dealing with positive integers. So from this we can compare the powers and the base. So from the base we get a strict inequality. Okay, so from this now we see that we can refer to this scenario where we have a number less than sum of two other numbers, then it has to satisfy one of these inequalities. So in conclusion, we must have that a raised to power p has to be less than 2 this, or a raised to power p is less than 2p. Okay. On this hand, we know that a is greater than b, and b is positive, so that means a has to be at least 2. So a is greater than or equal to 2. So from that, we see that we can now write this as less than or equal to a times a raised to power a minus 1, which is just a raised to power a. So by comparing power, we have that a has to be greater than p, and that contradicts the case we are looking at. So this is not possible. On the other hand, we have that since a is greater than or equal to 2, that this 2 raised to power p is less than or equal to a raised to power p, which is less than 2. So we have this. So if we divide by 2, we get this. And this is actually saying that f of p is less than 0, where p is this function we introduced earlier. Okay, remember this function was increasing and it's already 0 at 2, meaning that for it to be negative, it has to be less than 2. So this means that p has to be less than 2, and that's absurd. Okay, so either way, we just get a contradiction. So a cannot be less than p. So in conclusion, a has to be at least p. Okay. Based on this now, we could work with other estimates of p, because this is kind of like a bound for a. So this means that b factorial, which can be written as a raised to power p minus p, is at least p raised to power p minus 1 minus p, which we've bounded before. So we're going to make use of that now. So that is greater than or equal to p factorial. P factorial. Okay, so this means that b has to be greater than or equal to p. Otherwise, b factorial will be less than p factorial, because it just be a part of p factorial. Okay, so this we get the corresponding bound for b, and this implies that, in particular, that b is going to appear in b factorial. So that's p must divide b factorial. It's going to be one of those terms. Remember, b factorial is 1 times up to b, so p will be somewhere there. Okay, so we have this as a factor, and going back, we know this is equal to this. So it already divides b factorial and clearly divides p. So from what we did before, it has to divide the third part, which is this. And since p is prime, it must divide a. Okay, so this means that we can write a as some p times k. So k is positive integer. Okay, so since a is b times k, then we have that p squared has to divide a raised to power p, because p is at least 2. So p divides a, So p raised power p actually divides a raised power p. In particular, p squared divides this. But we have that p squared doesn't divide p. Okay, so among these three values, we know it divides one, doesn't divide the other, so you cannot divide the third, because if it divides two, it must divide all three. So this means that p squared doesn't divide b factorial. So what does this mean? Well, we have that as well, that if x doesn't divide b factorial, it has to be greater, right? So this means that p squared has to be okay, yeah, I think we could do better than this. Okay, so here we're going to show that it's going to be, excuse me. Okay, so here we can actually just show that 2p itself is going to be greater than b factorial. So it's going to be greater than b. It's going to be a similar idea, that suppose not, then we're assuming that b will have to be at least 2p. So meaning in the product expression of b factorial, we have p somewhere, and we have 2p somewhere, and possibly other terms. So we get a factor of p here, another factor of p here. So p squared will have to divide b factorial in that case, which is not the case. So we get this. So this actually creates like an upper bound for b. Once we have an upper bound for b, this suggests we can actually have an upper bound for a as well, because in terms of p, so suppose a is kind of like unbounded in terms of p, then b will have to actually be unbounded as well, and which is not the case. So from this, we suspect we can know something about how big a can be in terms of p. Okay, so what we're going to do now is we see that a raised power p is b factorial plus p. So this is less than or equal to this factorial, because b is less than 2p and it's an integer. So we have this. And if you recall, we've estimated this as well, which is less than or equal to p using the AMGM. So this is what we had. Okay. And this clearly is bigger than the other. For instance, when p is 2, the power is already 3. So this is clearly bigger. So this is in fact less than 2 times this value, which is less than p times the value, which is 2 raised power p. So what this means is that if you take the pth root, we'll have that this is strictly less than p squared. And now remember, a is pk, so this actually gives us k is less than p in particular. Okay. Now suppose we have that k is not 1. Suppose k is not 1. Then there's going to be a prime factor. K is going to have a prime factor because it's not 1. So from this prime factor, we see that since q divides k, it must divide a, because a is k times p. So q divides a. And also, q is going to be less than or equal to k, and k is less than p, so q is less than p, which means that q as a prime doesn't divide p. So from this, we can refer back to this scenario again, where we have 3 aspects. If you have 2, you have to have the third. So we see that we have 1 and the other one fails, so clearly we cannot have the third. All right, so this means that q will have to be greater than b. All right, but remember that b itself, we already had a lower bound for both a and b, which is that they are both greater than or equal to p, right, up here. So we have that q is greater than b, and b is greater than or equal to p, and this is a contradiction, because q is supposed to be less than k, which is less than p. So we have contradiction here. So what does this mean? It means that in conclusion, k has to be 1. and in particular, A will have to be just P. So this way, we've actually narrowed down the value of A. So now we only have two variables to deal with, which is that P raised to power P is going to be equal to B factorial plus P. So now we're going to always write it in this way. Okay. All right. So this is actually familiar. So we're going to use it. So before we move on, we're going to just do something simple. So we'll check some values to see. We'll see that if we check the first few primes, we see that for 2 and 3, we're going to get solutions. So when P is 2, we get that B factorial will have to be 2, 2, 2. So this is 4 minus 2, which is 2. So B will be 2, and this will be a solution. So we'll get A, B, P, all will be 2. So this is one solution. Okay, so keep this in mind. And if P is 3, we get 3 is about 3 minus 3, 27 minus 3, 24. And this is actually 4 factorial. So B has to be 4. And we'll get solution 3, 4, 3. So this is another solution. So apart from this, if we check 5, we see that 5 is not going to work. So actually, we're going to claim that if P is greater than or equal to 5, then we cannot have this. Okay, so we're going to assume we have that, and we expect a contradiction. So the assumption now is that P is greater than or equal to 5. Okay, so since P is greater than or equal to 5, it means that in particular, the bound we used the bound we used up here, we can make it strict from what we calculated before. So here, once P is greater than or equal to 3, we can make that bound strict. So this gives us a way of getting just a bit better bound than we had before. So we have that B factorial is P raised to power P minus 1. So now it's strictly greater than P factorial. So B is strictly greater than P. So we've eliminated that B cannot be P itself. Okay, so what does this mean? It means that B has to be at least P plus 1. And B over 2 is greater than or equal to P plus 1 over 2, which is an integer. So if we take the floor, it means that this value here is greater than or equal to this. So from this, we could get the next step we want to deal with. So which is to explore the power of 2 that can divide this. So we'll have to look at it from 2 angles. From B factorial angle and from this, and we already had the necessary components, so let's just quickly refresh our memory. So we have the first part here for B will coming from this, and then the second part will be coming from this. Okay, so I'm just going to write them. So in conclusion, we'll have this chain of inequalities. So this is less than the power of 2 in B factorial, and we're assuming B factorial is P raised to power P minus P. And we can factor out P and see that P is odd, so it will not affect the power of 2 in what's remaining, which is this. So now we can use the the final piece we proved, which is that this will be 2 times this plus 1 plus 1. Okay, so this is what we have. So at this point, we're going to see that this actually restricts the values of P we could have, because here we have something comparable to P, but here it's like we're only looking at the powers. Somehow it's now greater than something comparable to P. So there are going to be only very few values of P that can satisfy something like this. So we want to create the bound. So we're going to take 2 cases. So we have case 1. So in this first case, let's say 4 divides P minus 1. Okay. So this means that P can be written as 4, let's say 4T plus 1. Okay, and T has to be greater than or equal to 1 since P is at least 5. And from that, we can simplify what we have above. So we have that p plus 1 over 2 will simplify to 2t plus 1. And for on the other end here, we have 2 value of 4t and 4t plus 2 plus 1. So here we see that 2 divides this number, but 4 doesn't. So this power here, we can get as most 1 factor of 2 from here. Here, 4 divides this, so we can pull out that to get 2 factors of 2 plus whatever is left in t. Okay, so doing that, we see that we get this inequality 2, 2, b2 plus 1 plus 1. And if we simplify this further, we'll see that 2t minus 3 is less than 2 this. Now mind you, they are all positive integers, at least non-negative integers. We can divide by 2. And then we can now take the floor of this. So we see that that's because we can look at this a bit more efficiently. Let's say this is greater than or equal to strictly greater than 2t minus 4. So this is greater than t minus 2. So since this is strictly greater than t minus 2, it means that as integers is at least t minus 1. Okay. So this means that the power of 2 in t is at least t minus 1. So if we take these powers, this will be the precise power of 2 in t. So it has to be, means that t is going to be this value times some odd number, which is going to be less than or equal to t. And this is familiar because this is just saying that f of t is less than or equal to 0. And from what we did before, if t is greater than 2, it's going to be strictly positive. So this means that t has to be at most 2. Okay. And the values, so t is greater than or equal to 1, but less than or equal to 2. So we have either 1 or 2. And the corresponding values of p is, so this is 4t plus 1. It's going to be 5 or 9. And clearly 9 is not a prime. So we just need to check for 5. So for 5, we have b factorial have to be 5 raised to the power 5 minus 5. And this is 5 raised to the power 4 minus 1 here. Difference of 2 squares can help us simplify this faster. This is 26, and has a factor of 13. So this means that 13 will have to be a factor of b factorial. And so that means that b will have to contain at least 13. Now this is not going to work because we already had an upper bound for b. Recall that 2p divided is greater than b. So, and 2p is, in this case, is 10. So this is a contradiction. Okay, so in a very similar way, we're going to look at the second case. So that is where 4 doesn't divide p minus 1. Remember, p is odd. So if 4 doesn't divide this, we see that 4 will have to divide p plus 1. That's because p minus 1 and p plus 1 will have to be congruent to 0 and 2 mod 4. Either way. Okay, so because these are the only even numbers we have and they're not congruent. So one of them must be a multiple of 4. So must have this. All right. So from this, we just do everything the same light. So we have this t. This time will have to be at least 2. Because if t is 1, p will be 3, and that p will have to be greater than or equal to 5. So that's a contradiction. So we start from 2 this time around, and just very similar to what we did here, we'll make use of this inequality here, and plug the values. All right, so p plus 1 over 2 in this case will be 2t. So that's equal to 2, the evaluation of p minus 1, which is 4t minus 2, and the evaluation of 4t plus 1. So here we'll get 2, just like what we did before. 2 here. This 4 doesn't divide, but it's an even number, so we get power of 1 here. So ultimately we have that this minus So let's see, this minus 5 minus 4 is less than or equal to this. Okay. Okay, so this is what we have, and this means that t that well we raise just like what we did before. If you raise this should be less than or equal to t. Okay. So what we have now is that we have this. I think it's similar to what I had before, but I think it's actually different. So we're going to have to adjust what we did before. Okay, so we're going to take a new g, and we'll just quickly prove what we need. So now we'll consider g of t as a function to be this minus t. Okay, so we check that g of 3, g of 2, this will be negative. G of 3 is going to be equal to 2 raised to power 2 minus 3, which is 1. So this is positive. So if we can show that this is increasing from 3 and beyond, then we are good to go. So this minus g of t would be 2t minus 2 minus 2t minus 4 plus 1, similar to what we had before. And this would be 3 times this plus 1. And this is always positive. So this is actually always an increasing sequence. So this from the fact that g of 3 is positive, it means that g of t will be greater than 0 for t greater than or equal to 3. But here we see that we must have g of t to be less than or equal to 0. So this means that t is less than or equal to 2. Okay. And also we had that t is greater than or equal to 2. Here we have t is less than or equal to 2. So t has to be exactly 2. And p will have to be 4t minus 1, which is 7. So we just need to check for 7 this time around. So now we have b factorial should be p raised to power p minus p as 7, 7, 7. We can factorize this once again. So we can look at this as a difference of 2 squares. Okay, so next we can factorize 7 minus 1 out and 7 plus 1 out to get an idea of the factors. Okay, so from 7 squared plus 1 is 50, so this is actually 43, for example. This is 57. So this means that 43 is going to be a prime factor of b factorial. So as 43 divides b factorial, and once again, I'll say that this is too big because this will imply that b has to be at least 43, as 43 is a prime. And this means that 2p is greater than b is greater than or equal to 43. And 2p here is just 14. So we get a contradiction. Okay, so this is a contradiction for either cases, which means that we've proved our claim that p cannot be greater than 5 if it satisfied the solution. So we have two solutions now, which is A, B, P, 2, 2, 2, or 3, 4, 3. We're done. So this we don't need to check because they already checked when we're doing this. So we already checked them here. So this brings us to the conclusion of this. I hope you enjoyed this. So I'll see you in the next one. Bye.